Hello and welcome to the second 181 video on support vector machines. Today we'll be talking about soft margin classifiers. So our motivating question today is, for a hard margin classifier, we assume that the data was linearly separable, which is to say we can draw some sort of hyperplane boundary to divide the data up. But what if this is not the case? Consider the data below. We have one category of data in blue, one category of data in red, and clearly we cannot draw a linear boundary to separate this data. So our hard margin classifier won't actually work. But can we take the ideas of a support vector machine and still use them? And the answer is yes, and that's what we're going to talk about today. So the high-level idea of how we will develop a soft margin classifier is we're going to introduce a slack term to allow us to be a little bit off. By that I mean, in our hard margin classifier, you might recall that we required the condition that yn times w transpose xn plus w naught is greater than or equal to 1. But in this case, we will require the same condition, except it can be greater than or equal to 1 minus our slack term. And there'll be one slack term for every data point. So in our visual example here, let's say that this x here is misclassified by 2 in the wrong direction. Then we can make the slack term 3 here in order to allow for that to happen. Note, when I say it's off by 2 here, I don't mean absolute difference 2. I mean the unnormalized difference, because this thing right here, in order to get the overall difference, we should divide by the norm of w. But that's just a little bit of a technicality. So then we'll take all of these slack terms and we'll add them into a penalty term in our objective function, which is to say we are allowing for you to misclassify points, but if you misclassify points, we're going to penalize you for doing that. So that will tell the model to not want to misclassify points, even though it's allowed. Great. So here's the equation that we're going to start with. It's very similar to our equation for the hard margin classifier, and I will explain the differences. So again, we are taking the minimum over w naught, and in this case also our slack terms of 1/2 times the norm of w squared, which we had before. And now we're adding some constant c times the sum over all data points of the slack variables. So this is what I was saying by adding a penalty term. So the slack variables, and I'll demonstrate this later, but the slack variables are going to be 0 for correctly classified points, and they're only going to, for correctly classified points that are outside the margin, and it's only going to be non-zero for points that are correctly classified but close to the decision boundary, or incorrectly classified points. So here we're just penalizing the objective function for misclassifying or being close to the decision boundary. And then we're going to impose the condition that for any data point, yn times w transpose xn plus w naught is greater than or equal to 1 minus the slack term. And also, we want the slack terms to be greater than or equal to 0. Otherwise, for points that we classify really, really well, we could make the slack term negative, and then it would lower the loss, which is not something that we want to happen. So what exactly is the slack term? Let's demonstrate some things about it. So if we correctly classify a point and we're at least 1 away from the decision boundary, then I claim that the slack term is going to have to be 0. Now, why is that true? Well, this if this equation star holds, then this equation circle will also hold. And so then we want to minimize the objective function, and since the slack term has to be non-negative, then that function is minimized if we make the slack term equal to 0. Now, note that if yn times w transpose xn plus w naught is less than 1, so in this case, it could be correctly classified, but within 1 of the decision boundary, or incorrectly classified, then to ensure our condition, our condition circle, we have to make our slack term at least 1 minus yn times w transpose xn plus w naught. Right? Mathematically, that's the only way that this inequality will hold. So we obviously don't want to make our slack term any higher, because that will just increase the loss. So we use the lowest possible slack term that we can, but we have to make it greater than 0 in order for the inequality to hold. So we see here that the slack term allows us to misclassify points, but it will penalize the model and push the model away from doing so. So the other thing to discuss is our constant C. Note that our constant C is the coefficient on the penalty term that we added. And I claim that C controls essentially how much we care about violations of the constraint. So if C is really high, then our model will care a lot about misclassified points, points that are within the within one of the decision boundary. And if it's low, it won't care about that stuff as much. So a higher C will lead to more close fit to the data because it's going to care a lot about these slack terms. Whereas a lower C means that the other term in our objective function matters a lot more. And our other term in our objective function is essentially a regularization term because it's the L2 norm, or it's the norm of W squared. So that means that that term will dominate more and there'll be more regularization because that's what that term does. So depending on what you want, you can choose a value of C that's appropriate. So now I'm going to go ahead and go through the math. The math is pretty similar to the hard margin classifier. So I would recommend that you pause the video and try it out for yourself here. Also, I don't think that it's integral to the course. So if it's something that you felt like you understood the first time through and don't really want to see it again, it's probably fine not to watch the rest of this video. So we're going to go through this together. The first thing is, if you remember, we took our objective function and we essentially added Lagrange constraints and enforced a maximum and then enforced a minimum on top of that in our hard margin classifier video. And we demonstrated that the stuff that maximizes this is the exact same as the things that maximize our original equation right here. And if you recall from the hard margin classifier video, the way that we showed that our essentially Lagrangian equation and our constraint equation will give us the same answers was by first showing that the Lagrangian equation will only return W naught and slack variables that satisfy the constraints, and then by showing that when W naught and the slack variable are restricted to the constrained areas, that this Lagrangian will, when we do this outside argmin, that will be minimizing over the objective function, which are these first two terms that we're actually trying to minimize in our constrained optimization problem. So let's show that again. Suppose this first constraint is violated, which is to say that for some data point, yn times w transpose xn plus w naught is less than 1 minus the slack term. Well, in that case, for one of the terms in this sum here, the value of this will be negative, and that means that we can just make our lambda arbitrarily large, and then we're subtracting an arbitrarily large negative value, which will make make the inside term for those values of w naught and the slack term arbitrarily large. So obviously that won't be chosen by our outside argmin. And if the second term is violated, which is to say there's a slack term that's less than 0, well, then we can just make that Rn arbitrarily large, and for the exact same reason, that won't be selected. So essentially for any W naught and slack term that don't satisfy the constraints, the value of the inside parenthesized function in the Lagrangian is infinity, so it won't be chosen. Now, let's say the constraints are satisfied. Well, in that case, if let's take the simpler constraint first. If the slack terms are all greater than or equal to 0, well, then here, since we're maximizing, then and the RNs are restricted to be greater than or equal to 0, then all the RNs will be 0, so this term will just go away. And similarly, for this term, for every data point, either yn times w transpose xn plus w naught is exactly equal to 1 minus the slack term, in which case those terms of the sum will be 0 because this thing right here will be 0. Or if that's non-zero, then we know by the inequality that that will be a positive value. And so since we're maximizing over lambda, then lambda n, since it also has to be greater than or equal to 0, will need to be set to 0 in order to get that maximum. So this term will also disappear. So we will just get the actual true objective function when we use w naught and the slack term that do satisfy the constraints. So we see that these are the exact same thing. Great. So again, we'll take the dual, which is to say we'll flip around our maximum and minimum. And remember, there are certain conditions that need to hold in order for this to happen, but in this case they do. So then we're going to follow the same steps as last time. First, we're going to evaluate the middle part. We're going to take the gradient with respect to w. And the first thing to realize is that most of these terms don't depend on w. So when we take the gradient, they're not going to contribute to it. So we'll just get rid of them. So that has no w dependence. This has no w dependence. This has no w dependence. That has no w dependence. Neither does the last term. And so we're actually left with the same gradient as from the hard margin classifier. This first term just is w. This second term is sum over all data points of lambda n, y, n, xn. That's equal to 0. And then we can solve for w right here. Now we'll take the derivative with respect to w naught. Again, most of these terms don't depend on w naught, so I'm just crossing those out. And we'll end up, again, with the exact same derivative as we did in the hard margin classifier case. And we'll end up getting that 0 is equal to the sum over all data points of lambda n, y, n. Now, the last derivative that we have to take, and this is where we are a little bit different from the hard margin classifier, is the derivative with respect to the slack variable, because we're taking the minimum over that. And so, again, we get rid of any terms that don't depend on the slack variable, and we'll end up getting, so we're taking the derivative with respect to the slack variable for some, and this notation is actually a little bit confusing, so let's go ahead and take the derivative with respect to some, let's use j as an index since we're already using n as an index. So in the c is just a constant, and then the derivative of this with respect to just one of the slack terms is just going to be 1, because most of the slack terms have no dependence on the j slack term. So only the j slack term in that sum has dependence on it, and the derivative of that with respect to itself is just 1. Then here we get sum over all data points of lambda n times slack variable of term n. So again, the only term in that sum that matters is the jth term, and that's going to give us lambda sub j. And similarly here, we're going to get minus rj. And I'm just going to refer to this as equation 3. And we can rewrite this as rj minus c, equals c minus lambda j. And we know by choice that rj is greater than or equal to 0. That's how we defined it. And so that means that since rj is equal to c minus lambda j, then c minus lambda j must also be greater than or equal to 0. And that implies that c is greater than or equal to lambda j. So that means that we know that every lambda j, by definition, is greater than 0. And we just showed that it must be less than or equal to c. So this condition is another condition that we know must hold. Great. So now we substitute everything back into the original Lagrangian. A lot of this is going to be the same as the hard margin. Notice that the first term, these two underlined terms in black, are the exact same from our hard margin, and we're just substituting in for w naught and w here, which we got the same exact results for as the hard margin. So I'm not going to redo that math here. I'm just going to, well, it's the same thing. So we get the same results, and we get these first two terms. And then everything that we haven't used yet is the sum for all, c times the sum of all the slack variables, and then we have the sum of the lambdas times the slack variables, and the sum of the rn's times the slack variables. So we can actually put that all together into one sum, and it's the sum over all data points of c minus lambda n minus rn of the slack variable. But remember, by equation 3, this thing in parentheses is equal to 0. So this is 0, so then this overall sum is 0. So we actually just get the same result as we did for the hard margin classifier. So the dual problem is we want to maximize this over, well, it should say lambda on the left-hand side here, but we want to maximize this subject to the constraint that lambda is greater than or equal to 0. And note that we originally had an r in this too, but since there is no r in our final equation, we're not maximizing over that because r won't change our actual equation. And then remember, we have the same constraint as we did from taking the derivative with respect to w naught. Then we also have this other constraint that we got from taking the derivative with respect to r. And that dual problem now defines the solutions of the soft margin classifier. So the last thing that we want to do is find the intercept. This is similar to at the end of what we did with the hard margin classifier. It's going to be a little different here. So recall when we created the Lagrangian equation, we demonstrated that first that it wouldn't return w naught and slack variables that didn't satisfy the constraints, and then we showed that for the constraints that these two terms would be 0, right? So for any valid solution that this thing returns, that the last two terms are going to be 0. And we showed that by showing something a little bit more specific, which is to say that for any n, this is equal to 0, right? Because if the constraints are satisfied, then this thing is greater than or equal to 0, which means that if it's equal to 0, then clearly this entire thing is equal to 0. And if it's greater than 0, since we're taking a maximum over lambda and we're going to subtract this, this means that lambda will be equal to 0. Similarly, we showed that for any data point, Rn times the slack will be equal to 0 because subject to the constraints, the slack is greater than or equal to 0. And if the slack is 0, then obviously this is 0. But if the slack is not 0, then Rn will also be 0 because we're maximizing over R. And again, it's a negative there. So this is actually, says a specific name. This is called the complementary slackness, but it will be helpful for solving for W naught. So recall that we solved for the lambdas in, once we solve the dual problem, we'll have the solutions for the lambdas. And lambda, as we said earlier, is restricted to being between 0 and c inclusive. But I claim that for all intensive purposes, for some point, at least one, we'll have lambda strictly between 0 and c. It's technically possible that this won't happen, but that's a very, very rare scenario. And if that does happen, then the problem is essentially degenerate, and literature says that basically the SVM will just predict the majority class every time. So for all intensive purposes, we can assume that this sort of thing exists. We can also smallly perturb the actual model itself by changing C a little bit too. And so if it doesn't work out the first time, then you just bump C a little bit, and you can have a lambda such that this condition holds. So recall that we showed that C, for any data point, C minus lambda I minus Ri is equal to 0. Remember, we showed this when we were differentiating. That's this condition right here, condition number 3, when we differentiated with respect to the slack variable. And so that means that we know that Ri is not equal to 0 because lambda I is not equal to C. So thus Ri must not be equal to 0. So then by complementary slackness, this condition here, that means that the corresponding slack variable must be equal to 0. And so now we also know that lambda I is not equal to 0. So again, by complementary slackness, this time by this first equation, we know that the other part of the equation, the other part of the product, must be equal to 0. In particular, we know that this slack variable is equal to 0 anyways, so we can rewrite this as yi times w transpose xi plus w naught equals 1. And then we can multiply everything by yi. Recall that yi is either 1 or negative 1. So yi squared here just gets rid of the yi. And then we get this. We're going to go ahead and solve for w, and that gives us a solution for w. So that's how we would solve for w naught. And now let's talk a little bit again about the prediction, because it's very similar to the hard margin classifier. So remember that we're going to predict this value, and based on the sign of that value, we'll either assign it to the class 1 or class negative 1. And substituting in our formula for w, we get this. And here we see again that we can use the kernel trick where we replaced an inner product with a kernel that is much faster to compute. And also recall that a lot of these lambda n's are going to be 0, so this sum isn't actually really over all the data points, it's only over some of them. And so overall, that's soft margin classifiers. They're pretty similar to hard margin classifiers, but a little bit more flexible.